Okay, continuing with the light waves study guide. So now we're going to look at angle of incidence and angle of refraction. Okay, this is these are Snell's law. So Snell's law, we've got a material, we'll call it N1, and then we've got a second material, a different material, N2. This is the boundary between them. We've got a light wave coming in. We're always going to have like a imaginary perpendicular line with Snell's law. And so we've got a light wave coming in through one material that's in one. And then as it comes into the other material, it's going to bend. Okay. So it's going to bend somehow as it comes into the material N2. We've got an angle here called the angle of incidence. We usually call that theta 1. And then this is the angle of refraction, theta 2. And Snell's law says that N1 sine of theta 1 equals N2 sine of theta 2. And remember these signs here, these are just numbers, okay? These are not, something to be stressed about, okay? So how do these compare in the following scenarios? Okay, so let's say that light goes from air. So it's going from an N1 into water. N equals 1.33. So remember the N value tells us about density. Okay, water is going to be denser than air because it's got a higher index of refraction. So that means as my light ray comes in through the air and then it goes into the water, it's going to bend more towards the perpendicular. Because it's going from a less dense to a more dense medium. Okay, so this is less dense going into more dense. That's generally going to make my angle of refraction lower. Okay, but what's really happening is this light wave is bending. So wave bends more towards the normal or the perpendicular line. If we've got like the opposite case, we've got light going from a diamond. So here is N equals 2.49 into air. So we've got a more dense material. So let's say our light waves come in. This one is going to bend away from the perpendicular. If you're going from more dense to less dense, the wave is going to bend away. Wave bends away from the perpendicular line. Okay, so your wave its speed is changing as it's going from one material to another, and that speed change is really what causes this bend. And then that speed change, how much that is, depends on whether you're going from a less dense to a more dense medium or the opposite of that. Okay, now this next question, we're going to use Snell's law. So you're trying to figure out an unknown substance. Okay, so you're shining a light through this substance at different angles. So here you're shining this light in. So we're going to be in air in our N1. We don't know N2. And we've got some different angles of incidence and angles of refraction that we can use here, okay? So we'll just use the first one. We'll say 1 times, and I'm using this equation up here, N1 sine theta 1 equals N2 sine theta 2. So N1 sine of 15 degrees equals N2, I don't know that, sine of 8.41. Okay. With Snell's law, always make sure you're in degrees on your calculator. Okay. That was one issue I had with this borrowed calculator was that it was in radians, and I had to figure out. So to solve this, okay, we're going to solve for n2. We're going to divide the sine of 15 by the sine of 8.41. Oh no, my pen is dying. Okay. Don't put the 1 in. I saw a lot of people last week doing 1 times. First of all, you don't have to do that because you know that 1 times something is something, right? So don't do that. Also, that's going to confuse your calculator. It's going to think you're trying to do something different. Just do sine of 15 divided by sine of 8.41 equals 1.77 is what I'm getting. Okay. And if I look at this table, this is super small, but let's see. 1.77 looks like sapphire. Okay, so it looks like sapphire. We can double check this by doing another one of these. Okay, and then I got to find another pen. So let's try the sine. Let's be clear. Okay, so let's try the sine of 30 divided by, so 30, 16.41. Sine of 16.41 equals, again, about 1.77. Okay, and I should get the same thing if I do this third set of angles, which I'll just not do that in the interest of time. But it looks like the most likely identity for this substance is sapphire. Okay, which is a type of gemstone. So with Snell's law, so important notes, always be in degrees. Watch how you put it into your calculator. Don't do too many or too few parentheses. Don't use the 1. You don't need the 1. And get your setup figured out. Like, make sure that you're matching the correct n values with the correct angles. You're always going to be given the angles, and you're going to be given one of the n values, and you're solving for the other one. So just make sure you've got those straight. I think those are the big things. Drawing a picture is always helpful. I know y'all don't seem to like to draw pictures or write things out, but you really might be better off if you do that, because that will help you keep everything straight. Okay. So moving on from Snell's law, now we're going to talk about diffraction. Okay, this is that simulation that we did in PhET, okay, where we talked about what another wave type behavior. Okay, so what does it mean when a wave diffracts? So let's say we've got a light wave and it's coming up on like a slit. Okay, so these are like a barrier. This is like an opening. As the light wave goes through this, so it's having to go around these barriers through the slit, it's going to bend. It's going to curve around. Okay, and that's called diffraction. So a wave bends as it goes around an obstacle. And other types of waves, not just light waves, do this. Okay, other types of waves diffract. Sound waves diffract. That's why you can hear your friend if you're coming down the hallway and they're around the corner, because the light waves bend, as they go around the corner. So this is diffraction is a bending of the light wave. Okay. Okay. What changes during diffraction and what stays the same? Okay, so the wave, none of the properties of the wave are changing during diffraction. Okay, so what stays the same? All the properties of the wave. So frequency, wavelength, speed, none of those change. They all stay the same. What changes is just the direction it's going in, because it's going to bend. Okay, so your wave it's the same wave, same properties, whatever kind of wave this is. It's just now, instead of going along in a, I don't know, kind of like a straight line type path like here, it's bending or curving. Okay. So we looked at this double slit experiment, which was one of those big experiments where scientists learned more about the nature of light waves. And we looked at these like patterns that were formed on the screen. This is something you should go back and look at if you didn't do it in class or didn't pay attention, because it's important for this unit. But what's responsible for producing the light and dark bands? That is interference. 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 Okay. So remember, we talked about constructive and destructive interference. So the light, the bright bands are constructive, where our waves are combining. Okay. And then the dark bands are destructive, where our amplitudes are canceling out. So you got these, you've got light, if you, even if you've got one light source, as it goes through these two slits, it's making an interference pattern. Okay, as it ripples more and more and more, the waves are interfering with each other. In some cases they're going to combine amplitudes and you get these bright bands. In other cases they're going to cancel out and you get these dark bands. And then how does changing the distance change the pattern that you would see? So let's say we've got these light waves. We've got two slits that they're passing through. On our screen over here, okay, we're going to have some bright bands and some dark bands in between them. I guess I should have made the dark colored, but whatever, I'm labeling it. Now, if we make these slits farther apart, so I'm going to try and draw that. That's not great, but if we make these slits farther apart, we're going to end up, because these are all like ripply, patterny interference as it bends, and I'm not drawing this very well because this is the more important part. When you increase the distance, you're going to get more bands, but they're going to be narrower because you've had more time, I guess, for the waves to interfere with each other. So your number of bands increases, but they become narrower. It's because the interference pattern is different when we increase that distance. Okay. And again, that's something you should go back and look at. That's something I'll talk about during our review as well. But okay, this video is really long, so I gotta stop.